moisture content in the air, and it's also to some extent it's also sensitive to temperature. So if you want to maintain the output, you must maintain the temperature and humidity inside the textile mill at a required level. So this requires some kind of an air conditioning system which can keep the conditions at the required values. Also there are other industries like photographic industries which require again controlled temperature and humidity. So as a result, refrigerant systems were used in air conditioning system to maintain the required conditions. The first air conditioning system was installed by Eastman Kodak, the famous photographic film manufacturer, in 1891 in New York, to store photographic films. As you know, photographic films are very sensitive to moisture and temperature, so you require proper storage conditions. So this is the first example of air conditioning system. In fact, air conditioning systems were also introduced in movie theaters and in stock exchanges and all for providing human comfort, that is what is known as thermal comfort. Then the first domestic air conditioning system was installed in 1894 in Hamburg. Then in 1904, Willis Carrier has designed a central system using air washers, and in 1922 the same Willis Carrier has developed a centrifugal compressor for use in air conditioning systems. For his contribution to air conditioning industry and air conditioning science, Willis Carrier is known as father of air conditioning. Now let me show the basic principle of a vapor compression refrigerant system. Again you have the four basic components here: evaporator, compressor, condenser, and an expansion valve. Let us begin at this point. Right after the expansion valve, a low pressure, low temperature liquid enters into the evaporator, where it boils by taking heat from the surroundings. So surroundings get cooled and you get a refrigeration effect in the surroundings. So as a result of this heat transfer, liquid becomes vapor, and this low pressure, low temperature vapor is compressed to high temperature and high pressure in this compressor. So the compressor compresses the vapor to high pressure, so that as it flows through the condenser, it can reject the heat of condensation to the surroundings, and again it can become a liquid at this point. So at this point still you have a high pressure liquid. So the high pressure liquid, again its pressure has to be brought down, so it flows through an expansion valve where it gets throttled and its pressure and temperature drops to the required level. So this is how the cycle continues, and as long as the compressor runs, you get a continuous refrigeration output. This could be the refrigerant system of a typical air conditioner. For example, in a room air conditioner, this portion is kept inside the room, whereas this portion is kept outside. So the room air gets cooled and the heat rejection takes place to the surrounding air, surrounding outside air. Okay. Now let us look at another type of refrigerant system, that is known as vapor absorption refrigerant system. You might have noticed that in vapor compression refrigerant systems, the energy input is in the form of mechanical energy to drive the compressor. And the principle of refrigeration is the evaporation of a volatile fluid. In vapor absorption systems also, refrigeration is obtained as a volatile fluid evaporates. However, the basic difference between a compression system and an absorption system lies in the fact the very fact that in a absorption system you don't use a mechanical compressor, you use what is known as a thermal compressor. So the main energy input to vapor absorption systems is in the form of heat, not mechanical energy. So let us look at the developments of these systems. In 1810, John Leslie has demonstrated the basic principle of vapor absorption using water and sulfuric acid. Now when you keep water in contact with sulfuric acid has a high affinity for water, so it can absorb the water vapor formed above the water. So it as long as it has sufficient potential, it can continuously draw the water vapor from the water. Since this is an evaporation process, heat has to be supplied, so rest of the water gets cooled. That means using the principle of absorption and the high affinity of the absorbent, you produce a evaporation effect, and thereby you produce a refrigeration effect. This is the principle of vapor absorption refrigeration system. However, the process shown by Leslie is a discontinuous process. That means once the sulfuric acid becomes saturated, there won't be any more evaporation. So if you want to make it a practical system, you have to have again a continuous system. That means again you must have a cyclic process. So this is what is known as a vapor absorption refrigeration cycle. The first vapor absorption refrigeration cycle was suggested by Ferdinand Carr in 1860. He has used ammonia as the refrigerant and water as the absorbent. This is a very important invention, and aqua ammonia systems are very important, and they are also used even today. And in 1878, Windhausen has developed a continuous water sulfuric acid vapor absorption systems. In these systems, water is the refrigerant and sulfuric acid is the absorbent. However, sulfuric acid is corrosive, so later sulfuric acid is replaced by lithium bromide. So water lithium bromide systems have been developed. Again, water lithium bromide systems are very important because they are used today for providing air conditioning in large installations. And in 1922, two Swedish undergraduate students, Platen and Munters, have invented a very interesting vapor absorption system which does not require any mechanical device. That means it is a pumpless vapor absorption refrigerant system, and it requires only heat input for its operation. That is why this is called as a pumpless vapor absorption refrigerant system. And in 1926, Einstein has patented a pumpless vapor absorption system. This is also a pumpless system, but its principle is dramatically different from the one suggested by Platen and Munters. Now let me show the working principle of a vapor absorption refrigerant system. You can see that compared to the vapor compression system, the three components, condenser, expansion valve and evaporator, are common between these two systems. The only difference lies here. In a vapor compression system, we had a compressor here. The compressor was compressing the low pressure vapor to a high pressure. Whereas in vapor absorption system, instead of a mechanical compression, we have an arrangement which produces the same effect. Let us see how this is done. Here, instead of mechanical compressor, we have a component called absorber here, and a component called generator, and a solution pump. Let me explain the working principle here. Again, let us begin right after the expansion valve. After the expansion valve, we have low temperature, low pressure liquid, and this low temperature, low pressure liquid enters into the evaporator, where it takes heat from the surrounding water in this case and produces refrigeration effect in the surroundings. And during this process, the liquid becomes a vapor. Now what happens is, when this vapor comes in contact with the absorbent in this absorber, since the absorbent has high affinity for water, it absorbs the water vapor. That means this absorbent continuously draws the water vapor from the evaporator. So you have a continuous generation and continuous drawing of withdrawal of the water vapor from the evaporator. This is like the suction of a mechanical compressor. Then what happens is, as the absorbent absorbs water vapor, it becomes strong in refrigerant. So what we have to do is, we have to make it again weak. So how do we make it weak? Using a solution pump here, we compress this strong solution, that means strong in refrigerant, to high pressure using the solution pump, and then we pass it on to a component called generator. In the generator, what happens is, you supply high temperature heat to the solution strong in refrigerant. When you supply heat to the solution, refrigerant and absorbent get separated. When refrigerant and absorbent get separated, refrigerant vapor flows to the condenser, and since it is at a high pressure, it condenses in the condenser and forms a high pressure liquid which flows through the expansion valve, and the cycle is completed in this way. And the solution, which is now weaker in refrigerant, has to go back to the absorber, so it flows through a heat exchanger, and then its pressure has to be reduced. So we have an expansion valve here, where the pressure of the solution is reduced from the high pressure to the low pressure. So the low pressure solution, which is weak in refrigerant, goes back to the absorber. So the cycle is completed. That means a combination of absorber, solution pump and generator replaces the single component compressor in a vapor compression systems. And you can see that here the major input is in the form of heat. So these systems are very convenient, very advantageous, where you have abundant sources of waste heat. For example, you can use solar heat, or you can use waste heat available in industries for providing refrigeration. So absorption systems have their own advantages. And you can see that in this particular absorption system, a small amount of mechanical energy is required to run the pump. But compared to a compressor, the work required here is very small, because the work input is equal to integral VdP, where V is the specific volume and dP is the pressure difference. So since we are pumping a liquid here whose specific volume is very low, the required mechanical energy here is almost negligible compared to the heat energy. So this is the principle of vapor absorption refrigeration system. Now let us look at the plate and Munter system. As I was mentioning, a plate and Munter system is a pumpless system. That means you don't find any mechanical pump in this system, and the total pressure of the system is constant. That means at every point the total pressure remains constant. If the total pressure remains constant, how do you get refrigeration in the evaporator? So this is done by introducing a third gas, hydrogen. This third gas is inert. Okay, so when you introduce that into the system, it doesn't react with any of these other absorbent or refrigerant. So this third gas is confined to the low pressure part of the circuit. That means it is confined to evaporator and absorber. So because of the presence of hydrogen, what happens is that even though the total pressure remains constant, the partial pressure of the refrigerant reduces. That means you know that the total pressure is equal to partial pressure of the hydrogen plus partial pressure of ammonia plus partial pressure of water vapor. So if you introduce sufficient amount of hydrogen, you can see that the total pressure is constant, so the partial pressure of ammonia has to reduce. That means ammonia will be boiling at low pressure. Okay, so this is what produces the cooling effect in the evaporator. And here you can see that the major input is in the form of heat only, and here we use a component called bubble pump for pumping the solution from a low level to a high level. And these systems have many advantages. For example, since you don't have any mechanical component here, they are extremely reliable, and they are also silent in operation. That is the reason why these systems are typically used in small domestic refrigerators, in hotel rooms, etc., where you need a silent operation. So the use of these systems is mainly confined to these kind of applications. However, they are not used in large systems because their efficiency is typically very low. Now let us look at solar energy based refrigeration systems. Right from 1950s, people have been trying to use solar energy for providing refrigeration. Actually, this is a perfect match. If we can use solar energy for providing refrigeration, it's a good match, because the availability of solar energy matches with the demand for refrigeration. For example, on a hot day you require refrigeration. On a hot day, sun is available. So this is the motivation for developing solar energy based systems. So solar energy can be used in two ways. You can use it directly in the form of heat and have a vapor absorption refrigerant system. And you can also convert solar energy into electricity using, for example, photovoltaic cells, and use the electricity to run a motor and a compressor and use a vapor compression refrigerant system. That means solar energy based systems can be either compression systems or absorption systems. So as I was mentioning, the development began in 1950s, and it really picked up since 1965s. And the major reason behind this is that people have realized that our fossil fuel reserves are really limited, and refrigeration is a typically what is known as a low grade application. And it is said that for low grade applications you should not use high grade energy like electricity. Okay, it's like for example, you want to buy something in India and you have rupees and dollars in your pocket. Obviously it makes sense to spend rupees, not dollars. So it's similar analogy applies here. When you want refrigeration and when you have low grade energy is available, you should use low grade energy for providing refrigeration rather than wasting non-renewable fossil fuels. This is the main reason behind developing solar energy based systems, and as I said, it started in sometime in 1950s. Professor G.O.G. Lowe of America is one of the pioneers of solar based energy refrigeration systems. And the very first, I am just giving you a few examples. USSR has developed a 250 kg ice per day system using parabolic solar collectors. There are different types of solar collectors. You can have flat plate solar collector, parabolic solar collectors, and other concentrating type solar collectors. Depending upon the type of solar collectors that you use, you get different temperature outputs. So they have used parabolic solar concentrators, and they have built an absorption refrigerant system which could produce 250 kg of ice per day. And the first solar air conditioning system, that means solar energy was used to run a refrigerant system, which was then used for providing air conditioning, was developed in Queensland, Australia in 1966. Now let us look at another common and important type of refrigerant system, that is known as gas cycle refrigerant system. This gas cycle refrigerant system is slightly different from the vapor refrigerant system. In vapor refrigerant system we call it as vapor cycle because in those cycles like vapor absorption and vapor compression systems, refrigeration is obtained as the working fluids undergoes a phase change. For example, in the evaporator, liquid becomes vapor, and in the condenser vapor becomes liquid. That means the cycle involves two phase change processes. So that is why we call them as vapor cycles. Whereas in the gas cycle, the cooling is obtained because of sensible cooling. So that means there is no phase change involved here. So this is the difference between a gas cycle system and a vapor cycle system. And the major principle behind gas cycle refrigerant system is that there are basically two principles. The most important principle is that when a high pressure gas expands in a turbine and produces external work, its temperature and pressure drops. So you can use the low temperature air or low temperature gas for providing refrigeration. That means you first compress the gas to a high pressure and then allow it to flow through a turbine where it can do external work, and in that process it can reduce its temperature and pressure, and this low temperature low pressure gas or air can then be used for producing refrigeration. This is the principle of gas cycle refrigeration. Let us look at some of the developments. The first gas cycle refrigerant system was developed by John Gorey in 1844. Actually, John Gorey is not a scientist, but he was a doctor. Not a scientist means he is not a mechanical engineer or a refrigeration engineer, but he was a doctor, and he, while treating his patients suffering from fever, he was in need of large quantities of ice, and he had difficulty in getting ice using any of the natural methods. I mean, the natural methods, as I said, are not reliable, so ice was sometimes it was not available. So as a result of this, he has decided, or he wanted to build a system which is independent of your external circumstances and which guarantees a continuous provision of ice. Now, so this led to the development of the first gas cycle refrigerant system. And even though he has proved the principle and he has built a system, we really do not know the commercial fate of these systems. Even though it is said that some of these systems were exported to other countries, they were not big commercial successes. After John Gorey, Alexander Kirk in 1862 has developed another gas cycle refrigerant system. This is a very important gas cycle refrigerant system, and this is very efficient also because this is based on what is known as a reverse Stirling cycle. We will see the cycles a little later. So this is based on reverse Stirling cycle, and it is quite efficient. And right now these systems are used in very low temperature cryogenic applications. And Bell and Coleman have carried out several improvements to the basic air cycle refrigerant system proposed by John Gorey. So sometimes air cycle refrigerant systems are also called as Bell and Coleman cycles. And Paul Gifford has perfected an open type of air cycle refrigerant system in 1875, and this open type systems are very widely used in aircraft air conditioning systems now. So let me show the working principle of an open type air cycle refrigerant systems. You have three major components here: a compressor, a heat exchanger, and an expander. So let me start at this point. Here you have an atmospheric pressure and low temperature air. Low temperature means the temperature is slightly lower than the surrounding temperature. So you have air whose temperature is slightly lower than the surrounding temperature and whose pressure is same as atmospheric pressure. So this air is compressed in the compressor to high pressure. So at the exit of the compressor you have a high pressure air. So because of the compression process, its temperature also increases. So it can reject heat in this heat exchanger to the cooling water that is flowing through the heat exchanger. So in the heat exchanger, the high pressure air rejects heat and its temperature drops. So at this point you have high pressure and warm air, not hot air but warm air. So this high pressure warm air then flows through an expander or turbine. So as it flows through the expander or turbine, it produces external work. since energy is required for producing external work, it takes energy from itself. That means its temperature and pressure drop. So what you have here is a atmospheric pressure and low temperature.